Hello everyone, myself Sudarshan GK from Sri Venkateswara College of Engineering, Bangalore. My USN is 1VE23EC 110, subject Network Analysis, subject code BEC 304, Department of Electronics and Communication. Topic: Classification of electrical networks. Introduction to electrical networks. Electrical networks are interconnected components that allow the flow of electrical energy. They can range from simple circuits with a few elements to complex systems with numerical components. They are essential for the distribution and control of electrical energy. Understanding their classification helps in analyzing the behavior and design. An electrical network is a collection of electrical components like batteries, resistor, capacitor, and inductor that are connected together. Definition of electrical networks. An electrical network consists of elements like resistor, capacitor, and inductor. They can be interconnected in a various configurations. These configurations determine the network's functionality and performance. An electrical network differs from an electrical circuit in that an electrical circuit requires all connections to be closed while an electrical network can be open. Types of electrical networks. Electrical networks can be classified into two main types, linear and nonlinear. Linear networks obey the principle of superposition and have constant parameters. Non-linear networks exhibits behavior that varies with the voltage or current levels. Linear electrical networks. Linear network consists of elements whose voltage and current relations are linear. Common example including resistive circuits and LRC circuit under small signal conditions. They are easier to analyze using techniques like superposition and Thevenin's theorem. Linear network is a network that exhibits constant parameters, resistance and inductance. Nonlinear electrical networks. Nonlinear network contains elements like diodes and transistors. They behave Their behavior is not proportional to the input voltage and current. Analyzing nonlinear networks often requires numerical methods or simulations. It consists at least one of nonlinear elements, not counting the voltage and current independent sources. Active electrical network. An active network consists at least one voltage source or current source that can supply energy to the network indefinitely. Active component is defined as an electronic component that supplies energy to a circuit and can control electron flow. All electronic circuits must contain at least one active component. Passive electrical network. Passive network is an electronic component which can only receive energy which it can either dissipate, absorb or store it in electric field or magnetic field. Passive elements do not need any form of electrical power to operate. As the name passive suggests, passive device does not provide gain or amplification. Passive components cannot amplify, oscillate or generate an electrical signal. Series electrical network. Components connected in series are connected along a single electrical path and each component has the same electric current through it, equal to the current through the network. The voltage across the network is equal to the sum of the voltages across each component. The series circuit is a circuit where the components are connected end to end in a line as illustrated in figure 1. Parallel electrical network. If two or more components are connected in parallel, they have the same difference of potential across their ends. The potential differences across the components are the same in magnitude and they also have identical polarities. The same voltage is applied to all circuit components connected in parallel. Series network characteristics. Series network have a single pathway for current flow. The total resistance is the sum of individual resistance. Voltage is divided among components based on their resistance. Parallel network characteristics. Parallel network provide multiple pathways for current flow. The total conductance is the sum of individual conductance. Current is divided among components based on their resistance. Time invariant and time varying networks. Time invariant network maintain their properties over time. Time varying network have components whose characteristics change with time. These classifications is important for understanding signal processing and communications. Ideal versus real network. Ideal network assume perfect components with no losses. Real networks account for particle factors such as resistor, capacitor and inductance. This distinction is critical for accurate modeling and simultaneous electrical network theorems. Various theorems assist in analyzing electrical networks. Key theorems including Thevenin's theorem, Norton theorem, and superposition theorem. These tools specify complex network into manageable form. Application of network theory. Electrical network classifications are crucial in circuit diagram and analysis. They help engineers optimize performance and efficiency. Applications include power system, communication, networks, and electronic devices. Software tool for network analysis. Several software tools assist in the simulation and analysis of electrical networks. Example include SPICE, MATLAB, and PSPICE. These tools provide visualization and help provide network behavior. Future trends in electrical networks. The rise of smart grid is changing how electrical networks are classified and utilized. The renewable energy sources are influencing network designs and classifications. Understanding these trends is essential for future electrical engineering practice. Thank you.